similar in certain manners. I will explain in which ones. This is joint work with Carlos Garcia's paper. So I couldn't resist showing this as my first slide. So I'm working on the N-vortex of the sphere, and here is the atmosphere of Jupiter, where you see these concentrated agents of vorticity that move around. Now, a disclaimer. What I would say has more of a mathematical interest than physical interest. So, but this is just sort of a motivation to study the N-vortex problem on the sphere. So let me start by giving an introduction to the N-vortex problem, taking into consideration that the audience might not be familiar with it. So Vortex Dynamics was born with this paper by von Helmont. So out of Euler equations, he manages to describe the motion of vortices, or concentrated regions of vorticity that move around on the fluid. So this is how it works. So you model point vortices simply by points. So we assume it's an idealized model where all of the vorticity is concentrated at given points and everything happens in 2D. So you have a certain number of vortices that move around, and associated with each of them you have vorticity, which is circulation around each of them, and they interact and move around. So the vortex intensity, that's the circulation around each of the vortices, that remains constant in time because it's a conservative model, so there is no viscosity, and this is constant. These vortices interact non-linearly and they move, and obviously the problem is to determine the position of the vortices starting from an initial configuration. So how do they move? So I try to make a picture showing you how they move. So imagine you have three vortices moving on a plane. Each of them has given vorticity. So I put one which is negative just to make it more interesting. And each vortex needs to tell each other how to move. So these vortices, they're going to determine a velocity field out of Euler's equations. And if you want to see how they move, well, what you have to do is switch off the influence of one of the vortices. So for instance, if you want to see how this vortex here would move, what you do is you turn on the fluid generated by the other two vortices, and that tells you, well, you imagine the vortex is just a test particle in the fluid and it'll move around. Similarly, the influence of the other two vortices tells you how this one will move, and same thing for the other. So in the end, the presence of the three vortices tells you exactly how the three of them are moving. So the equations of motion look like this for three vortices on the plane. So x and y are the Cartesian coordinates of the vortex, and you see they move around due to the influence of the other vortices that are there. So interestingly, these equations admit a Hamiltonian formulation. So this observation was due to Kirchhoff in 1876, and what you find is a Hamiltonian system with n degrees of freedom. So you see that you have a logarithm over there. Things blow up when you have collision between the vortices, and the presence of the logarithm there is due to the fact that the log is the fundamental solution of the Laplacian in the two-dimensional plane. Now, vortex dynamics becomes more interesting when you have some boundaries or the vortices are moving in a geometry. So a vortex can also interact with a boundary, and so it can self-influence its motion. Not only it's affected by the motion by the presence of the other vortices. So just to clarify this community, what are the differences? So with the, I guess it has to be the planar n-body problem because I'm talking about point vortices. So important thing here, there are no velocities or momenta. So once you prescribe the configuration, things move around. I don't need to tell you the position and velocity, the position and momentum. This determines the dynamics. And the phase space, I guess, for this problem of five vortices would just be the positions of them. So you have five vortices on the plane, then the phase space is just the Cartesian product of the plane with itself 5 times. And notice this is not a tangent or cotangent bundle, so it's just positions. The number of degrees of freedom is equal to the number of vortices, and something there's no Lagrangian formulation. So start out with a Hamiltonian formulation, which does not have a Lagrangian origin. Okay, so now let me tell you what the problem that I want to talk about is. So I'm considering the problem of n vortices on the sphere, and I assume each of them has all of them have the equal vorticity, and so they move around. So for the rest of the top, the sphere is just embedded in R3 as vectors of norm 1, and Vj tells me what's the position of the jth vortex on the sphere. So these are the equations of motion. This is how they move around with the appropriate normalization of the circulations. And these equations go back to these two authors in the 20th century. So I'm interested in looking at those equations. And well, first thing is that they have a Hamiltonian structure, because that's the problem on the plane. So they move around on n copies of the sphere, because they need each copy to tell me where every vortex is sitting at. And then the symplectic form of this phase space is just the sum of the area forms on each copies of the sphere. And the Hamiltonian also has this form of logarithm influence. So important thing here, the sphere is homogeneous, so a vortex does not interact with itself. So there's not a self-interaction. All of the motion is due to the presence of the other vortices. So this is a Hamiltonian system with n degrees of freedom, and there is a symmetry. So you put an inertial frame to see where the vortices are located, but the problem is independent of how you put this on. So there's a rotational symmetry, SO3, and there's some first integrals, which is just an instance of Noether's theorem. The center of vorticity, so-called, is an integral of the motion. So V1 to Vn are the positions, look at points in the sphere. Well, if you interpret them as points in R3 and you add them up, then this quantity is constant. So if you do symplectic reduction, namely you fix the value of the integral and you quotient out by the appropriate symmetry, what you find out is that the system is integrable if n is less than or equal to 3, or if the value of that integral is equal to 0. In any other case, you should expect periodic dynamics. So when n is equal to 4 or n is greater than 5, you should expect periodic motion, and all of these conclusions are independent of the fact that the vortices are equal. So even for different vortices, you expect this difference. So some similarities with the n-body problem, and here just the threshold of integrability to non-integrability is at 4, not at 3. Okay, so what is the problem now? So something that happens when you put vortices on the sphere is that you might find equilibrium configurations. So you might put them in a certain way in which the vortices will not move. So, if I give you n equal 4, 6, 8, 12, or 20, just by symmetry considerations, you think, well, if you put them at the vertices of Platonic solid, that's going to be an equilibrium and things will not move. So the question is the following. Well, before that, just the interesting thing is that the decahedron and the cube are unstable, but the other three are stable, which is, I guess, geometrically interesting. So the problem that I want to consider is the following. Are there families of nonlinear modes of oscillation arising from this equilibrium? So there's an equilibrium of a Hamiltonian system, so you expect there's some Lyapunov periodic motions around them. And the reason why this problem is challenging is that these equilibria are not isolated. So if you think about it, you can organize your vortices on the vertices of a cube, and that's an equilibrium, but the cube, you can put it around the sphere any way you want. So within the phase space, which is this large phase space, there is an SO3 orbit of equilibrium. So there's this 3-dimensional submanifold, which is field of equilibria. So if you do the linearization on each of these, you're going to find 3 zero eigenvalues, and you can apply Lyapunov-Spencer's theorem. So this classic theorem, Lyapunov, has further extensions, but none of them apply. And there's a recent paper which actually uses degree theory that Alessandro was talking to us yesterday, but they had to assume that for some reason that I don't understand, that the phase space is a Euclidean space, so the results also do not apply in our situation. So there seems to be no general theorem that will guarantee the existence of this solution. So that's what we're after. And the way we're going to solve the problem is by looking at solutions with a prescribed symmetry. So let me just tell you how this works in general. So what I'm looking at is solutions, certain equations of motion with certain symmetry. So this is just in general. So imagine you have a system of differential equations from a given manifold. You have a flow associated to it. And then I need to introduce the idea of symmetry. So what we have is a group action on the manifold. So there's a group transformations on the manifold, and I'm assuming that it's not free. So the action leaves some points fixed in the manifold. So suppose that the system of differential equations is compatible with the action. So that means that the flow of the system commutes with the symmetry transformations, or infinitesimally the push forward of this diffeomorphism defined by the group action leaves the vector field still, so it doesn't move it around. So in this case, there is a nice interaction between the solutions at the points that are not free by the action. So if you take a subgroup, which is usually taken to be discrete, of this symmetry group G, and consider the set of points in the phase space that are fixed by the action of all elements within the group G. So this is a subset of your phase space. Well, it turns out that it's easy to prove that this subset is invariant under the flow. So you start with an initial condition there, you stay there. So what you can do is simply restrict your dynamics to this set. So you pick your subgroup G, you identify these points, and then that's invariant. So let me give you an example of this in an example that probably you've worked on. This is an example that usually you find in courses in differential equations, because you have a system on R2 that is centered linearly, and then the nonlinear terms sort of give you instability. So the way you analyze the system is you pass the polar coordinates, and the variable is decoupled, so you know what R is doing, if that is just turning around. Well, the reason why you can decouple the variables is because there is an underlying symmetry. So if you consider the action of SO2 just by rotations on the plane, the system is invariant. So here I did a picture of it. So I drew the velocity field associated to that, the vector field associated to that equation, and I try to sort of indicate how the action is commuting to the flow. So you start at initial condition Z. First, you follow the flow, then you follow the group, you arrive somewhere. But if you first follow the group and then follow the flow, you arrive in the same place. So that's the symmetric commutation. Now, the action of SO2 on the plane has a fixed point. The origin does not move around. And just by this reason, the origin has to be an equilibrium point of the system. So the set of fixed points of SO2 is the origin. The origin has to be invariant under the flow, so it has to be an equilibrium point. So this is an instance of the theorem that you've probably seen before. Now, this all works very well in the context of Hamiltonian systems. So if you have a symplectic manifold and you have a Hamiltonian, then this determines a Hamiltonian vector field in the usual way. And now imagine that you have a D group acting on your manifold, which leaves the Hamiltonian and the symplectic form invariant. So the action is by symplectomorphism. Then, as a consequence, the Hamiltonian vector field that you get is equivariant. And the crucial observation is that now if you take a subgroup, then the set of fixed points is not just any subset of your phase space, but happens to be a symplectic submanifold. And then the restriction of the flow to this symplectic submanifold is obtained just by restricting the Hamiltonian and restricting the Hamiltonian form. So this subsystem that I indicated, that I talked about, is actually a Hamiltonian system. So how do we put this into action in our problem? So this is the problem that I introduced, and Vortex problem on the sphere, each of them moving with identical vorticities. And the symmetry group here, this is where the assumption that the vortices have equal strength is important, is the permutation group. So you can permute the vortices and rotate them around. So the action of G of this group on M is just simply permute the vortices and rotate them. Now this action is not free, so that's the reason why we can use discrete symmetries. So the groups K that I'm going to pick in the way I described before are built out of these finite subgroups of SO3. So these are classical subgroups. And if you pick any of these subgroups and you have a homomorphism from this subgroup into the permutation group, then you can look at the graph of this homomorphism, and this happens to be a subgroup of G, which is a twisted subgroup. That's the way it's called. So what the strategy is to pick fixed points of this twisted subgroup. So select your group K in a right way, then look at this fixed points space, and the idea is that this is going to be then a subsystem of the full system, and the idea is to pick the group K in such a way that this is a 1 degree of freedom Hamiltonian system. And if it's a 1 degree of freedom Hamiltonian system, then the generic trajectories are going to be periodic. So that's how we're going to find these periodic energies. Okay, so these ideas appeared before in the literature, and we sort of knew that this was the way that we needed to proceed, but we didn't really know what was the best way to implement these ideas. And then I was very lucky because I attended this seminar organized by this group, by Marco Fenucci, and then it was sort of clear how to do it in a way that I don't know if I would have ever come up with it. So, and then I sort of found this very interesting paper by Giovanni Gronchi, and so this was a great inspiration to implement all of these ideas into the problem. So what we define is pretty much what they do in their paper, which is look at solutions where you're prescribing the symmetry a priori. So you pick one of your discrete groups. Suppose it has order m, and you give an ordering to the group elements. And then what you say is, well, I'm looking for solutions of the problem in which the position of the first m vortices is sort of given by a generating vortex, which has position u of t. So this is what you need to determine. And the next ones are just obtained by applying the group elements G1 through Gm. So that gives you the position of the first n vortices. And then we allow ourselves the possibility of having some vortices that are fixed. So F1, Fm plus 1 up to Fn are some vortices that are sitting which do not move during the motion. Now, you can put those vortices that do not move as long as they have some, so they talk to the group K in a correct manner. So their interaction with the group K has to be a very particular one, and is that the set defined by them has to be K invariant, and it has to have non-trivial isotropy. So once you prescribe this, then you can find solutions of this form. So this is the theorem. You can find a solution of this form, provided that the set F is chosen in the way I said in the previous slide, and U of t has to satisfy this simple equation for it. So U dot equals minus 1 over m, where m is the order of the group, U cross the gradient of h, where h is this function. Now, you see this is a Hamiltonian system on the sphere with a weighted symplectic area form, but you're done. So these are the equations that we need to analyze, and all of the periodic motions that we find there are going to define periodic motions of the full system. So Arnold-Lubel theorem tells you that generic solutions are periodic. So the proof is simply to realize that the connected components of these fixed point sets are symplectomorphic to the sphere. So somehow U is parameterizing this fixed point space, and the restricted flow in each connected component is conjugate to the restricted system on S2. And something else that we were able to do in the analysis to recognize which symmetry is inherited by the restricted system out of the full system. And it has to do with the normalizer of the group K within SO3. So for the rest of the talk, I just want to illustrate this theorem for particular choices of the group K being the dihedral group and the tetrahedral group, and different choices of the set F. So for the purpose of illustration, I just want to say that you can easily regularize the system, because if all of the vortices have equal strength, so if all of them are positive, they cannot evolve into collision. So you cannot start with a configuration and go into collision. So for the system, you can regularize it very simple. So you just put collisions into the phase space as fixed points, and these fixed points are going to be stable because the energy is at the maximum over there, so it's infinite. So all of these collisions happen to be equilibrium points, which are stable. So this is the picture that you get when you pick your group K to be D2, and you're working with a 4-vortex problem, and none of the vertices are fixed. So let me try to explain. So this is the dynamics on the restricted space, or on the sphere, and associated. So this would be the motion. Each of these curves is the motion of the generating vortex. So imagine you're following one of these green curves over here. So that's what the generating vortex is doing. So the others are moving around the tetrahedron. That's because this equilibrium point corresponds to a tetrahedron. So these points over here correspond to squares. So if you're set up here, then the other vortices are positioned on an equatorial square, and that solution is unstable. And these heteroclinic orbits are simply connections from one square to another. So those are equilibrium points. And these solutions over here, there are equilibrium points in which you have binary collisions at the north and south pole. And so you have these solutions close to them, which correspond to these two vortices going in one direction, two vortices going on the other direction around the north and south poles. And then it's simply a matter of changing the group and looking at the solutions that you find. For instance, here you have 6 vortices moving around with D3 symmetry, and these points over here correspond to octahedrons. So these green solutions over there are going to give you some normal modes with D3 symmetry around the octahedron, and then there's a bunch of other periodic solutions that are illustrated. I think here the color code is consistent, so whatever you see in red over here corresponds to animation in red, purple, and so on and so forth. And just moving around, so interestingly here, you could put n equals 8, k equals to d4, then you find a cube inside of here, but this cube happens to be unstable. So instead of finding normal modes of oscillation around the cube, we found heteroclinic orbits connecting the cube to itself. And interestingly here, this is the cube octahedron, which is the sort of energy minimizer, so the configuration with the least energy with this type of symmetries. Okay, so we were able to formulate a theorem for this kind of symmetry. So when k is equal to Pn, F is the empty set, total number of vortices is 2n. And the theorem was just the classification of the equilibria in this case. So we were able to show that some of the equilibria that arise are when the vortices are organized on a prism. And interestingly, we found the height of the prism in a closed formula related to the Chebyshev polynomials that also appeared in the previous talk. So maybe, I mean, if you think about this as a continuum problem to the form of fluid with some discrete perturbations being the vortices, maybe the remark made by Francesco holds. Also, the antiprism, we were able to determine the height. So this is also a solution that arises, in which just the top part of the prism is rotated by half of the angle. And then we also found that the 2n polygon. And these are the only equilibrium configurations that can arise when you describe this kind of symmetries. Then you also have collision solutions where you have binary collisions on the vertices of an N polygon, or where half of the vortices are at the north pole and half of them are at the south pole. So once you have this, you may determine the stability. So antiprism and the collisions are stable, the other two are unstable, and then you can apply the Apunov's theorem on the restricted space to show, so this is a proof of existence of one parameter families of periodic solutions around antiprism solutions and polygon and polar solutions. Okay, now just for the purpose of it, just let me show another example. This is a solution in which you're fixing one vortex at the north pole and one at the south pole that do not move, and then you allow some symmetry. So here is a D2 symmetry, and the reason why I show this is because you find other modes of oscillation around the octahedron. So this is by fixing it. Here we found by putting 8 vortices also with two of them fixed at the north and south pole, we found normal modes of oscillation around the cube. So you just need, instead of putting the cube in a prism configuration, you put it with one of the vertices at the north pole, other at the south pole. What you find is an anti-prism, and this is you find some modes of oscillation. Here is D5. So the reason why I show that is because we find another Platonic solid. So this is icosahedron. So you find this normal modes of oscillation around these vortices. And then similar theorem, we were able to classify all of the equilibria in the restricted system, also in terms of Chebyshev polynomial for the height of the prism and antiprism. And that proves existence of one parameter families of periodic solutions, doing what's shown in the figure. So in the case of an antiprism, you have a single vortex that goes around each of the vertices, and polygons with poles. You have two vortices going around the vertices of a polygon, and similar for the last one. So just let me show you last pictures. What happens when you pick the tetrahedral group, you get even more interesting symmetries. This time the restricted space has an octahedral symmetry. That's why you see that picture with a lot of symmetry, and that's because the normalizer of the tetrahedral group within SO3 is the octahedral group. And this time what you find over there is the icosahedron here in these green solutions, and you have these normal modes of oscillation with tetrahedral symmetry around the icosahedron. And well, there's just many pictures that come up here. We can also classify what goes on here. Here then you find this cube octahedron, which happens to be an unstable solution. Icosahedron is a stable one. Truncated tetrahedron is unstable. And then you have some collisions. So you're working with a 12 vortex problem. So for instance, here you have tetrahedron, and you have three vortices colliding at each of the vertices. Your octahedron, you have a binary collision at each of the vertices. And according to this, you have these one-parameter families of solutions coming close to these figures in the way indicated in the figure. So last picture would be you pick F to be the vertices of a cube. And the reason why we did this was to find normal modes of oscillation around the self-decahedron. So the decahedron is sitting over here. The normal modes of oscillation corresponds to these little green rotations over here. And you see there is the vertices of a cube stay put, they do not move, and you have little oscillations around the remaining 12 vortices that build up the decahedron. So even though the decahedron is an unstable equilibrium for the system, you may find this solution. So here again, classify the equilibria. You have this cube of points which is fixed, and I tell you exactly what the remaining 12 vortices do and which ones are stable, which are unstable, which again give you one-parameter families of regular solutions. So I guess the conclusion is we found some of the normal modes of oscillation near the Platonic solids by fixing different symmetry groups and fixing some of the vortices not to move in certain cases. So this is, even though these are all of the normal modes or not, we haven't really looked into that question. And this is the reference that we just got published, this paper. And let me tell you in my last slide what we're trying to do. So for the purposes of understanding the dynamics near one of these solutions, well, it's nice to look at those small oscillations, so indeed they exist. But if you want to understand what is going on near the equilibrium, then perhaps the solutions that you should look at are not these normal modes of oscillation, but what's called a relative equilibrium. So for instance, let me tell you what this solution that you see in blue is over here. So I start with this equilibrium, I leave the north pole fixed, and the base of the triangle, I lift it a little bit upwards. So that's going to be a solution. That's an initial condition for a solution that rotates steadily about this point. So this is a relative equilibrium. If you instead put the vortices a little bit down, then they're going to start spinning in the other direction. And so you have this very, very slowly. Okay? This is happening very slowly. Obviously, the speed is the speed of the animation that we're seeing, which is arbitrary. So the way this is converging to an equilibrium solution is just the speed of oscillation is slowing down until you reach this critical height, and then you go up and you change the direction. But you can also find other types of equilibria if instead you so this edge of the tetrahedron and this one, you sort of move them apart in a certain manner, they also start rotating, in which you have this time two rings of two vortices which are rotating. Now, out of these four, it happens that this one is stable. So what we're trying to do right now is looking at the sort of, well, Platonic solids, for instance, but also for other arbitrary number of vortices, not very large, looking at the lowest energy configurations of the system, so the ground states, and trying to understand which are the relative equilibria that emerge from these solutions that are stable. And that we do employing just the geometry of the problem together with computer-assisted proofs. So one of the collaborators in this new project is Jean-Philippe Pisa from Montreal, who was an expert in this. So this is what we're working on, and I hope to something to report interesting on this. So thank you very much.